Hey everyone, my name is Professor Wasim Jabi, and I am a professor of computational methods in architecture at the Wells School of Architecture, Cardiff University. In this short talk, I will talk to you about graphs, space syntax, and urban movement, and how to understand streets as network and analyze them. So, cities are usually considered a network of connected spaces that influence how people move. And the main avenue by which people move is through the street network. So you'll find that streets are sometimes available for analysis, and maps are loaded digitally for them to be analyzed. So if you are thinking about streets as edges and the intersections of streets as perhaps vertices or points, so edges and points, you can use a graph as a formal way to think about a street network. So what is a graph? A graph is nothing more than a way to describe connections. A graph has a series of nodes or vertices, as they're called, and those are usually things like a room or a street or a person. And then these things or nodes are connected by edges. So edges represent a certain relationship, a certain connection. So, for example, rooms are connected by doors, streets are connected by junctions, or people are connected by social relationships. So, when we talk about social media and people are connected to each other, that also can be represented as a graph. So, graphs are nothing more than nodes and a series of edges that connect these nodes. So why do we use graphs? We use graphs to help us ask spatial questions. For example, which streets are easiest to reach, which streets many people pass through, or which streets connect many others directly. So instead of trying to find that from observation in a city, that's obviously an impossible task because it's a very big place to go and visit and document everything. So we represent the network as a geometry, and then we convert it into graphs, and then we can analyze those graphs. So graphs let us measure spatial importance. It tells us which streets are more important, which locations are more important than other ones, and not just to draw the geometry of it. So part of that, there has been a field of research developed in various universities. UCL in London, University College London, is one of the main places that this area of research has developed. And this area of research is called space syntax, basically how space is formed. The word syntax comes from, language, what are the rules that govern space, the rules that govern language, rules that govern space. So space syntax. So space syntax studies how spatial configuration affects movement. Okay, so by just looking at how a space is configured, to how it is connected, uh, you know, how dense it is, etc., you can derive or kind of predict how people are going to move in that space. That's the whole idea. That's the whole theory of it. So it treats space as a network and it uses graphs to analyze accessibility and flow. So space syntax helps you explain how pedestrians move, how people move. It explains wayfinding, meaning if you get lost, what are the ways to find the correct path that you need to follow. And also urban vitality means how are there urban spaces that are perhaps isolated, they are cut off from the main roads, or are they suitable for development? Let's say if you're trying to locate where a project should go, space syntax can help you analyze the urban space and the street network so that you can locate certain functions. So, in summary, space syntax helps you measure spatial potential, the potential to use the space in a better way. So, there are, excuse me, I have a cold, so excuse me for that. There are certain metrics, measures that we can apply to graphs, meaning that we can find out which nodes in the graph are more important than other nodes. How do they compare to each other? What is the hierarchy of nodes in the graph? Because they are not all equal. So that is usually called centrality, how central something is. But centrality is not geometric. It's not like the center of the city geometrically. It is just simply more central spaces are spaces that are perhaps better connected, or they are closer to more other spaces, sort of like they have better connections to other places, or more people pass through them. That's called betweenness centrality. So there are different types of centralities that you can measure in a graph. So centrality describes how important, influential, or strategically positioned a vertex or node or an edge is within a graph based on its relationship to all the other elements in the network. So centrality, as I said, is not geometric. It depends on connectivity and path, not physical size or length. So even when we're talking about how long it will take you from one node to the other, we don't measure it in distance. We measure it in the number of edges that you have to traverse, the number of hops, if you think of it that way, that you need to go through from one node to another. The actual distance does not matter. High centrality often correlates with movement, flow, or visibility in a spatial network. In urban and space syntax analysis, centrality helps explain why some streets are busier than others. And that's going to be part of your exercise to see if the digital analysis matches your experience and your field experiments or field observations. There is no single best centrality. Each measure answers a different spatial question. So the intuition tells us that centrality tells us which parts of a network matter most and why. Okay, so that's the issue of centrality. And now I will go and explain to you three different types of centralities that we are going to be introducing here and what do they show us about the city. So the first one is called degree centrality. Degree is nothing more the number of edges that are connected to a node. You can just simply count them. So if I go here to node A, and if I count the number of edges that are connected to it, I come up with the number 5. While node B has only one edge, and the rest C, D, E, and F, all of them, each one of them, has two edges. So they get a number 2. So as you can imagine, A is more central in terms of degree. It is the one where you have a lot of choice to go to all the other places, while node B seems to be more isolated. It doesn't matter where it is geometrically, just think about how well or how not well connected it is. So degree centrality, to define it, is how many direct connections, counts how many streets meet a street. High degree means that it has many immediate choices, and it's often found at busy junctions. So from here, the intuition is that from here I can go in many directions. That's kind of degree centrality. Another type of centrality is called closeness centrality, and it measures how close a node is to all the other nodes and takes the average of those hops, or as I said, number of segments that it traverses. So again, let's take a look at node A that has the number 1. Why does it have the number 1? Because from A, you only need to traverse one edge to go to any of the other nodes. So take a look at it. To go to B or C or D or E or F, you just have to do one hop. So if you do, that's 5. You divide by 5, the average, you get 1. 5 divided by 5. Okay? So from A, it only needs one hop on average to go to the other nodes. If you do the same exercise for B, you'll notice that it needs one hop to go to A, but it needs two hops to go to C, two hops to go to D, two hops to go to E, and two hops to go to F. So if you sum those up, you get 9 hops. You divide them by 5, you get 1.8. And the other nodes, you get an average of 1.6. Now, here, the smaller the number, the better, because that means you have less number of hops on average to get to the other nodes. So again, A comes up on top because it is central. It can go to all the other nodes only with one hop. And B is the worst one because it has to traverse many hops, many edges, in order to get to the other nodes. So just to read the slide, excuse me, how close is this node to all others? And as I said, closeness here is number of edges, not the length of edges. Doesn't matter how close or far they are. It's just the what we call the topologic distance, meaning the number of edges. It measures the average distance to every other node. Smaller number is better. High closeness means it's easy to reach from anywhere. The intuition here is that this street is centrally located in the network, obviously. So that's closeness centrality. So now we have degree centrality, number of edges connected. It's about choice. And this is how close it is to other nodes. This is called closeness centrality. The third and last one is called betweenness centrality. And that measures how if a node is between other nodes, that means it acts almost as a bridge, as a gateway to get from one node to the other one. So imagine, for example, you start from these different nodes and you walk around this network trying to get to the other nodes. What node gets traversed the most or on shortest routes? So for example, if I want to go from B to F, from here, B to F, I have to pass through A. There's no other road. I have to go through A. Same for from C to F, from D to F, from E to F, etc. So if you calculate these shortest distances, shortest path, they all have to go through A. So A gets a score of 16 because we count B to F and then F to B as well. So the reverse of it. However, the other nodes, B, C, D, E, and F, you don't have to go through them in order to get from one node to the other one. So if you just, in your mind, start doing a itinerary to go, let's say, from C to B, you don't have to go through F. You don't have to go through D. You discount the ones where the node is the actual destination. We're talking here only about nodes that you pass through, not the nodes that you arrive at. So it turns out that in between the centrality, A wins again with 16, but all the other nodes now get a score of 0. So they don't really have any betweenness. They're not a bridge. Only A is really a bridge. So high betweenness means it's a strategic connector, and the intuition is many people pass through here even if they are not staying. So now we have degree centrality, we have closeness centrality, and we have betweenness centrality. So what does this all mean? How do we use it in analyzing, let's say, central Cardiff? So basically what we do is we get the map of Cardiff or street network or any city. There is something called GeoJSON, which is a file format. Basically, you don't have to worry about it because we're not going to be doing that in this exercise. But basically, we start by having the streets represented as edges and the junctions represented as nodes or vertices. And from those, we build a graph, we analyze the graph, and we visualize the results on a map. This is the overall. But there is a little bit more to it because we don't want streets to be edges. We want them to be the thing. Remember, and we said that nodes represent the thing. So there is a little bit of a trick where we convert edges into nodes and nodes into edges. So we kind of do the reverse of this graph. And then we analyze it and then we map it back. So I'll get into that a little bit later. But basically what we are trying to do is we are trying to convert pure geometry into knowledge, into some kind of insight into the city. If we just look at this map, okay, we know that it is the network of streets in this city, but we don't have any insight. Where are the central spaces? How do people maybe move in there? We have to kind of analyze the graph of it in order to get some insight and some knowledge. So as I said, there is this little trick using something called line graph. And a line graph is basically something that converts an edge into a node and the nodes into edges. So as you can see here, edge number 5, I drew like a little bit of an arrow, becomes node number 5. And whatever it is connected to becomes edges. Okay? The two graphs might look similar. I mean, they drew them here in this example in a similar way, but they're not the same. I mean, the position doesn't matter, obviously, but you just have to realize that edge number 5, for example, is connected to edge number 6 and edge number 4, if you look on the left side. And of course, on the right side, you'll see that node number 5 is also connected to node number 4 and node number 6. And each of these nodes represent an edge in the original graph. So in standard kind of street networks that we get, the intersections are the nodes and the streets are the edges. So we reverse that logic so that each street becomes a node and connections happen at intersections. So we want to analyze the centrality and the importance of streets, not junctions. So we need to turn the streets into the nodes of the graph. Now, there's one more. This one gets a little bit even more complex, but you really don't have to worry about it. And it has to do with the fact that streets, because they are intersected by different streets, different routes at junctions, you might get different multiple segments for the same street. The street gets cut up into small segments. But we don't want to analyze every segment of the street by itself, because every segment might not be very important, but when you look at the whole street and what it is connected to and its kind of position in the city, the whole street from beginning to end is important. The classical example is Oxford Street in London. If you analyze Oxford Street just by its segments, it doesn't show up as a very important street. But when you bundle them all together and say, what is Oxford Street in its totality linked to, it becomes quite important, actually, quite central. So quotient graph is a very technical method that collects all the small segments as long as they have the same name or same ID in the database that's coming in from GeoJSON. It bundles them into one node. Even though there are multiple nodes, it says, oh, okay, so those 5 segments all belong to the same street. So let me compress them into one node. And what are those nodes connected to? We draw edges and we connect them to it. So you just don't have to worry about it. Just keep in mind that this is one way to deal with the street as one entity rather than multiple entities. So now is the time to run the centrality analysis. Here we are using a piece of software that I have developed for many years. It's called TopologicPy. It is based on Python language, and you can download it if you want and try it if you are somebody who knows about Python language. There are other piece of software. There's something called DepthMapX from UCL. There are other ones from the US. But here we are using TopologicPy to run the centrality analysis. So we imported the map from GeoJSON. We use something called Passover Turbo, I think. And we got the lines imported. And then we built a graph. We did the line graph, we did the quotient graph, and now we are ready to do the degree analysis and closest analysis and betweenness analysis. So each street gets 3 numbers describing its role in the city. Now these numbers, you can normalize them so that they are from 0 to 1, 0 being the least important, 1 being the most important, or not. It's completely up to you. What people really like to see are the excuse me, the color-coded maps, because they are a really intuitive way to look at the importance of streets and the spatial hierarchy of streets. So, for example, here, this is downtown Cardiff. The castle is in the upper left corner a little bit, where that street kind of wraps around it. The yellow street in the top is Queen Street, a part of Castle Street and Duke Street, and then Queen Street, and that's the area where all the arcades are, etc., etc. So by doing that kind of degree analysis here, these are the streets that have the most connections. You can find out. Don't worry about the top streets here. I think that is actually wrong. That's from a different analysis, so don't pay attention to that. But just if you take a look at the color coding, you'll find out that Queen Street is the one that is most connected. That's degree centrality. Closeness centrality, as you can see here, it's more like what I see here is a bit of a ring road, like a cycle, where they are bright yellow, and then in the middle it's less close, which is surprising actually. But those are the ones that are connected to a lot of streets. Okay. Again, Queen Street becomes one of the main ones, and then there are other streets. I have given your professor a an Excel spreadsheet that has all the correct numbers and street names, so you can compare it with your own observations. And the last one is the betweenness centrality. As I said, betweenness identifies streets that act as bridges, as main connections. And again, Castle Street and Queen Street, as you can imagine, act as a bridge that gets you from one part of the city to the other part. And there are two other streets at the bottom. As you can see here, they get you from one part of the city from the south to the north. So it is highlighted in yellow. And the other streets have darker colors, so they're less important as bridges. So once we do, excuse me, once we do all of that, we take the color coding and the lines and we superimpose them over the original map in order to be able to find out what streets are what. And we color them where the brighter colors means they are more central. So we have now the same city but three different readings. We have degree, things about this is about choice. Where are the streets that you have the most choice to go in different directions, and which streets kind of give you very limited choice in where to go? Closeness centrality means what streets are really more central in the city, and from there you can get to many other places really quickly. And that might be a place to put, let's say, a bus station or something, because you can walk from there to other places, or you might want to put a hospital there because people can get to it really quickly because it's close to everything else. And then which streets act as major bridges, major connections. You want to make sure that those are wide enough not to have congestion. And as we know, if you've ever driven on Castle Road and Duke Road, getting through the center, it's very congested because everybody has to go through there. It's basically a bottleneck. But this tells you that, and we didn't tell it that Castle Street is anything important, but through the analysis, the software discovered that on its own, just by the connectivity of the streets. So here I tried to put it back by superimposing. It's a little bit dark, so apologies for that. But if you look at it carefully, behind the degree centrality color coding, there is the actual map of Cardiff. I tried to match it as closely as possible so that you can read the street names and compare it to your own observation. So this is the degree centrality. This is the closeness centrality. And this is the betweenness centrality. And that's it from me. I hope you have enjoyed this talk, and good luck with your field observations. Thank you.